We have mentioned controller design with exam model knowledge, and today we will extend the same model but with unknown parameters, or the model knowledge is not available. Then the approach or the controller to be designed to deal with this property is high gain control and high frequency, or adaptive control. Okay. So today, at the beginning, I will first quickly go through the material we covered last time. So give you a recap on what we have taught on Monday. Okay. So on Monday, we say that we consider this kind of Euler-Lagrange system, which is like a robot arm system. A single joint, so the Q here is a scalar. Okay, and the parameters are known. They are constants. The states and the time derivative of states, which are the angles, are measurable. So everything here is known. And we try different Dilbert functions. We try 3 different Dilbert functions, and only the third one works. So, but it requires using a filter tracking error here. Okay, filter tracking error. So R is defined as E dot plus alpha E. Alpha is also can be considered as a control gain. Okay, E is the error, the tracking error. So the property of this R with E and E dot is that if R is bounded, both signals will be bounded. If R is L2, both signals are L2, right? If R converges to 0, both will do, okay? And we try option 3, where V is designed as a function of R squared. And then we go through the stability analysis. We first take a time derivative. And then we can, in this E double dot, it comes with Q double dot inside. So we can substitute the closed loop dynamics here in the bracket, right? And that's the time that you can include the controller tau here to design the controller, right? Because you want V dot to be negative definite, but this structure is not negative definite. You need to find a way out, right? So we can design tau, maybe cancel out some nonlinear terms and create some feedback terms. And in the next few slides, in the next topic, we will also introduce cross terms. Okay, so here just let me ask you a question. So what will you design with this controller? Your controller here is tau, right? You have all this stuff, and the simplest way is to cancel this term out, right? You move the obstacle here. This is the obstacle that prevents you to show V dot is negative definite, right? So the simplest way is in the controller, okay, in the controller here, you design this controller and put all these terms in a box and repeat here in the controller, right? And they have different signs, so they will cancel out. This term and this term will be canceled out, right? And after it cancel out, you also add a feedback terms, right? And this feedback term plays an important role because the minus KR here, which comes from the controller, with another R in front of the bracket, can make V dot to be negative definite, right? So that's the way we design this controller. So this is probably the most simplest nonlinear controller design because everything is known. Remember, everything in the controller have to be known, right? So you need to verify that it's known, right? It's the acceleration of desired trajectory, right? Or angular acceleration, right? So it's known, it's by design. G is known, L is known, right? Because L is a known constant, it's a known parameters by assumption. Sine Q is known because Q is the angle, the joint angle, which is measurable, right? You can obtain by sensors. This is obtained by predefined signal. And eta is measurable because eta is Q d dot minus Q dot, right? Q d dot is by design. Q d dot is by design. Q dot is computable, right? And KR is also known because R is designed as a combination of E and E dot, right? And K is the control gain. So after you design this controller, you substitute into here, you got, and you regroup and cancel out some terms, you got V dot to be ND, right? So everything is great. V is PD, V dot is ND. You got a asymptotic, global asymptotic stable or global asymptotic tracking, right? Because it's a tracking problem. So R converges to, so it's asymptotic tracking. So R, and here only shows R converges to 0, and that implies using the previous, the property in the previous slide, imply both signal will go to 0 as t go to infinity. Okay, so this is from the previous lecture. So today, right now we're going to introduce unknown parameters, system with unknown parameters. So what is unknown? M is unknown. You don't know the inertia. You don't know the length, the L, right? Which is the associated geometry of the link. So M and L are unknown. Okay. So this kind of dynamics, this kind of nonlinear system can become complex, you know. And the controller can be more hard to design if you assume system parameters are unknown and maybe Q dot is unknown. Q dot is not measurable. You only measure Q, right? But you control Q double dot. You know what I mean? Only Q is measurable. Q dot, Q double dot is not measurable. Not measurable. That would be more tough than this problem, right? This problem only assume parameters are unknown, okay? But the signals are still available or measurable, okay? So if this is these two parameters are unknown, how will you design the controller? Everything changes, right? If it's unknown, let's go back to this slide. If n is unknown, okay, then your controller, you have to implement something that's unknown, right? And you cannot do that, right? How can you write a code, design a controller, implement a controller, and which is unknown, right? There's no way. So you cannot use that structure. The controller had to be redesigned. So how will you design a controller? So first here, let's repeat. The objective is to do tracking control, okay? And we want the joint or the state Q to track a desired trajectory, QD dot and QD double dot. And they are bounded. They are designed to be bounded, okay? And they are known values because they are by design, user's choice. Okay, and want E to be bounded, at least bounded, but if you can find E converge to 0, that would be great, right? That would be even better. But because we are discussing the unknown parameters, sometimes the error could not go to 0, okay? But at least you need to design a controller that can ensure the error will be bounded. Okay, bounded means you still have some tracking error, but it's bounded. It doesn't go to infinity. Okay, the tracking error will be close to 0. This is also acceptable as a controller. So the step is the same. You define the error signal. Okay, take the time derivative, check if control input appears in here, and because here it doesn't appear here, because you only see q dot, right? And from the dynamics, tau is equal to something. Tau, the control input, is equal to something, and it's a function of q double dot, not q dot. So you need to take one more time derivative until you see q double dot. Okay? Because q double dot implies the control here, and only you apply the control, you can design it in a stability analysis. Let's design the robust control for unknown system parameters. Let's go step by step. Okay, tracking control. Here's the problem definition. So let's define the error tracking signal and filter tracking error. Constant. Open loop dynamics, according to that, we divide it by m on both sides of the equation. You got, and move the second term to the right. You got q double dot equal to G sine q. And that's a minus. So this is the open loop dynamics. And let's say we design a design controller as tau as a feedback term, kr, because r is now the filter tracking error. You can consider it as a new tracking error, okay, plus robust terms to be designed, okay, and you substitute into here back to the open loop dynamics, you got closed loop dynamics. Okay, this is closed loop dynamics. Something weird here. Okay, something weird here. Right? Because when you design the above function, now we only put r because we want to. So in the above function, we only see r or e. Yeah, in other words, only see the filter tracking error or the tracking error, not q anymore, right? We don't put v equal to minus mq squared, right? It's different, right? If you put this, means your intention to show is, okay, is nd, which means probably q squared nd, right? And you're trying to show q goes to 0, right? Agree, right? But here we are not doing regulation, we are doing tracking, which is this, right? We are doing this, okay? But every signal in the above function will be eventually proven to be 0, right? So that's why if this is your objective, you should. That's why we design the error signal here, because we want error signal converge to 0 eventually, right? 对不对 ？Tracking problem. So this structure. So that's why we design this liberal function. So the next step is take the time derivative of the above function. And here you will see the time derivative of the signals, right? And there is no way either R dot or E dot give you the access to substitute your control input, right? To substitute your control input into here, right? To use this equation, there's no chance given this V dot, right? Because you find there's no Q double dot in here on the right hand side, right? 懂吗？听得懂吗？你不是要把 control 带进去分析吗？因为你要设计 control 嘛，你要怎么设计就根据 V 大让它是 ND 嘛，所以你要把 torque 放进来嘛，你要把 control input 放进来，对不对？那你怎么放进去？用这个 equation 啊，因为你知道有微分的地方就是有机会带进去嘛，因为你 V 大嘛，所以这边 signal 都微分了，那就是你唯一的 chance， right？ Here's the chance because you have time derivative. Here's the chance that you can substitute the Q double dot where you have control input here, right? 对不对 ？But there's no Q double dot, right? See? Maybe, well, it's in here and in here, right? It's in R and in E. Why? So let's take a look in here. So we introduce open loop, closed loop. Now get into here. V dot is, we design V, start from V. V is right? And we take the time derivative, we got RMR dot plus alpha square M alpha square E M E dot. So we did not see Q double dot, right? But it's basically Q double dot is in here. So you need to expand this, which is, what is R dot? R dot, according to the definition R dot, you take one more time derivative. You got R dot equal to E double dot. E dot, right? And here it comes with Q double dot, right? Because Q double dot is inside E, okay? So when you take the time derivative, that's E double dot plus alpha E dot. And this is alpha square E M E dot. Okay. Then you span this. You span this. That give you, which is Q D minus Q double dot, right? Plus alpha E dot. Okay. Now you can substitute this closed loop dynamics here, and you will get this. Okay. You will get this. See? So now it's now become clear how we will design this tau, this torque, right? So next step by experience is we expand this signal out, okay, which is using this relation. Okay. Because the reason is if you don't span out, if you don't expand this, there's no way you can cancel this out. Okay, there's no way you can cancel these two terms. They are different. But after you expand, they can be cancelled. Okay. Here and here. Okay, these two terms can be cancelled, and that the reason is I expand eta here, so you can cancel this term out. Otherwise, there's no way you can cancel it out. Okay, so now from 5 to 7, from step 5 to step 7, we are doing regrouping. Okay, regroup. You can cancel some terms, and some terms were left, right? And you can regroup the whole equations. So next, and we also substitute our control into here, right? We substitute tau into here, which will result in these terms. And this r is coming from this r in front of the bracket. Okay? So next, we are almost done. Next, by observation. How do you observe? Well, you will see every term will have r or e, right? Because eventually you design your reliable function as a function of e and r, right? To prove v dot to be nd, you need e squared, r squared, right? So you want to create e squared, r squares. So by observation, r squared and minus r squared is a good term, right? Plus something r squared is a bad term, right? But they can be combined, right? If I choose control gain large enough, maybe larger than alpha m, okay, they can be a negative. So there's a chance to be negative definite. So it's r squared term here, and here is the e squared term minus e squared term. So it's highly likely to be a good result for v dot, right? So let's try. But here the problem is here. You see r, right? You see r. It's not r squared, it's only r. And r and this is a known term, right? It's known. Okay, it's no. M is unknown, right? M is unknown. L is unknown. So basically this term is unknown, right? So we can upper bound these terms, okay, by a constant C1. Okay, but this C1 might be large because it had to be greater than m times q d double dot. Q d double dot depends on the trajectory you're trying to follow, right? Okay. But it's reasonable that you assume you can upper bound this whole term because q d double dot is assumed to be bounded in the very beginning, right? Back to here, the assumption here is q d double dot is bounded. right? So it can be upper bound by a constant. That's why you can upper bound the summation here by a constant. So we can upper bound the whole term in the bracket by a constant, positive constant C1, right? Agree, right? No matter it's negative or positive, it can be upper bounded by C1. Okay. So now there's another question. I say R M Q D plus N G L sine Q. Okay. So, sorry, let me repeat steps 7 here. So I have a question for you. MQ Okay, this is step 7. So question for you. Can you design, this is originate from, this is basically U, right? This is U. We design U as this. And the design of this can probably prove this to be ND or at least an SD. Okay. And maybe you need to choose some gains, K, for example, K greater than alpha M, right? Because K, here's a negative term, here's a positive term. You need to choose. The gains have some conditions to be satisfied to guarantee stability, right? But can you design maybe another term called plus some terms that cancel out this term? Can you? Probably you want to do this, right? Can you? If you can, what would be the term in the bracket? You might want to, oh, here it has R, right? It has minus and R. Here it has plus R. So maybe you design this in the bracket, right? Okay. Then you might be genius, right? God, I never thought about this. You must be Einstein, right? So what's the problem with this? Obviously, it doesn't work. Why? You know why? 有人可以告诉我为什么不行吗？ So it looks great, right? It looks you are smart, Einstein, right? Next Einstein. But if you so you put this and this term can cancel out this term. Oh, amazing, right? Everything becomes square, and it probably will be ND, right? But it doesn't work out. Why? The problem is in the not in the analysis. Okay. The problem is not in here. The problem is in the control. Why? Yeah, that's right. That's the problem, right? Remember I say every term in the control in the U have to be known, right? You cannot implement something you don't know. You cannot, if it's an unknown system, if you don't know inertia, you don't know the mass of the system, you don't know the mass of the car, how can you implement a controller that require that information? You don't know what's the mass of the robot arm. Can you put that mass in your controller implementation? No. Right? If you are control car 10 kilo, okay, you want to apply a force, or in this case, maybe it's robot arm, right? We controlling this joint, we apply a torque and want to do something, and here is have inertia, okay, M or inertia here. In this case it's M, right? But M could be generalized to inertia. Okay. Anyway, this is unknown system, right? And in your controller, you say controller can be designed as KR plus VR plus all this guy, right? The problem is I don't know M, I don't know the mass. How can I put, you need to implement this in your computer, in your processor, right? And this is the required parameter to be designed. You don't know the mass. How will you implement? Do that? Right? So you see the problem, right? No next Einstein, right? Just joking. So that's the reason we design this as a controller. Okay, we don't know this, but we let this VR take care of the uncertainties. Okay, and before, at the beginning of this class, we say we can do that. You can do that because M is known, right? In the previous case, M is known. You can do that, and that's the most easiest nonlinear controller design. But not now. Okay. So now we design the controller. Let's see how we can do the analysis. We can upper bound the terms. Now go back. How will you upper bound these terms? It's a scalar, right? V is scalar. Everything here is scalar. So scalar can be positive or negative. What's the upper bound? Can I say it's upper bound by, we know this is a, can be upper bound by constant, right? C1, which is positive, greater than 0, okay? C1 is greater than 0. Can I say C1? Is it true or not? If it's true, raise your hand. If false, raise your hand. Give you a counter example, okay? Negative, positive, negative. Sorry, negative. It's unknown, right? If this summation is negative, okay? Negative, but this time is negative, is still upper bound by C1, which is positive. That's correct, right? This upper bound is still holds, right? But the product of this will change the sign, right? So if R is minus, R is the state, you cannot control states. And this is, if this is minus, okay, and R is minus, R here had to be minus. And you upper bound a minus start by C1, right? So it's correct term by term, R by R, this by C1, but the product will be different story. Okay? So you cannot do that. But what is correct? If you do this, that will be correct. Okay? Because the product will always be positive, right? But you need to do this because you don't know. R is the states. It could be positive, it could be negative. You cannot control. You don't know because you don't know the solution, right? You don't know the trajectory of R. You don't know the solution. Do that. It's nonlinear system. So next. So that's why next step. Next step, I change equality to inequality and put absolute value on R. Okay. And regrouping the terms, okay, we put minus kr squared here, put this term here, and VRR here, and this term here, okay, and that's almost done. So we have minus r squared, right? We have minus r squared. And you need to choose we have these two terms. This is good term. Right? Okay, but here there's a condition for it to be a good term if k is greater than alpha m. Okay? So you need to implement your controller k large enough, at least greater than alpha, which you can is a user choice. M is the unknown, right? Unknown mass. So, but it's still feasible, right? You choose if you control the robot arm, for example, right? And you can usually by design, you know, approximate mass of the link, right? So, for example, by observation, probably 10 kilogram, right? You can put the upper bound can be, you know, you choose k to be alpha and put 15. As long as it's greater than 10, it will be fine. Okay. If it doesn't work, then you change to 20. Eventually, it will work, right? By the tracking error, you can observe. So that's feasible. Okay. So good terms. Now bad terms, which is positive, right? Always positive, because already put the upper bound, absolute value. So the approach now is to design this to dominate this. Okay, and VR, what is VR? VR, well, it's basically the same. VR is designed to be some KR. Here is a constant. Okay. And the reason to design as this structure have some reasons. We want to use least robust term to deal with this term, right? VR is robust term. Robust term is used to deal with uncertainties. And where's the uncertainties? Here. And uncertainties can be upper bound as this. Okay, so robust term is used to deal with this. Although robust term VR is designed same as feedback control, right? Same as the KR here, the term before VR, right? They have the same structure, but the functionality is different. Okay, so that's why I put K3 C1 squared here. K3 C1 squared is another constant. Okay, and you will understand why I put in this structure in a few minutes. So let's do these two terms. Let's try complete a square. Okay, and this is Chinese. Okay, Niels, are you coming to Taiwan for learning Chinese, or is that that's the partial reason?
Yeah, I'm trying to learn.
Okay, so you know these 3 words? No? It's hard to know. It's terminology. So, yeah, complete square. So, 大家知道吗？很久以前的嘛。So basically, it's this: a y square by。我相信我只写这个，你们不知道是什么东西嘛，对吧？所以我才写配方法。OK， 所以只写这个你们很害怕嘛？写的配方法就觉得哦，那个害怕程度从这边降到这边，是不是？然后大家眼神都充满了安全感。OK，so 这个要怎么用呢 ？So how will you do this? So basically, this is the A. In our case, there's a minus here, okay? And want to use completely the square to put into some minus square term plus some plus terms, okay? Which is 4a b square. Here is y minus ab, okay? Remember, right? 这样写有没有错 ？2. Okay. Long time ago. Right? So let's try this. Y square plus aby minus. 对不对？ plus 2ab square, right? And plus 对不对？是吧？ So this equal to this, okay? By observation. Okay, so this. So now, use that to upper bound these 2 terms. Okay, this term is minus k3c1 square. You will understand in a few seconds why I put square here. R square plus c1r. Okay. And you can consider this. Absolute value of r squared is equal to r squared. Okay. And use that. You can get minus. So by comparing, the A here is what? Is K3 C1 square. Okay? B here is not equal. Let's say this. B is C1. Y is okay, is equal to y, which is r minus 2a, so it's 2a k3 c1 square, and b, which is c1, okay, square plus 4a 4k3 c1 square b square c1 square。 这样会不会怪怪的？ 4a square b 平方 c1 square. Okay, that should be right. Yeah. So it cancels c2 1 squared, c1 squared, so it's 1. Okay, and plus these two terms minus k alpha m r squared minus e squared. Okay, 这样 OK 吗？ Okay, so this term is always negative, right? It's not e squared term, it's not e squared term, it's not r squared term, but it's always negative. Okay, so we can further upper bound a negative stuff by 0 and repeat whatever left. So 4k3 minus k alpha m r squared minus okay. So same as this. How do you interpret this? So this is constant. Okay, it's a constant depend on K3. So the constant can be decreased by increasing K3. Okay. And if you don't consider these third terms, the first two terms can make the system negative definite, right? But when you have this term, it becomes UUB, okay? It becomes UUB, okay? And as we say, R will eventually be bounded. This can be used to conclude R will eventually be bounded. Okay, UUB, right? R is the very R and E, because R and E is a signal in the Diabol function. So R and E and R will be bounded. Okay, so your tracking signal will be bounded. Okay, so now let's now plot the Diabol function. Upper bound is not equal. This term not equal to this. This term upper bound is. And can zero upper bound something that's negative? 可以吗 ？Zero 是不是可以 upper bound 任何负的东西？所以这个可以被 zero upper bound， 因为这里不是 equal sign， 它是 upper bound。OK， 这样没问题吧 ？Right？ And you can drop it zero， 你就可以不写。So they become that. Okay. So let's plot V. So the initial condition of V depends on the initial condition of R, right? Depend on initial condition of E and the initial condition of R, and that E depends on QD0. minus Q0， 对不对？ So sorry, let me again. So initially, you design some trajectories, like sine function trajectories. Okay, it's QD. Okay, and initially, your Q is here. Okay, your Q0 is here. This is QD0. So the difference of these two is the error, right? This is the error. So error is here. E0. Okay? And you implement the controller, right? You implement these controllers in your closed loop dynamics, in your system, okay? And you get a closed loop dynamics. So you don't know the solution of Q, but you know the analysis tell you that E eventually will be bounded. So E eventually will be somehow bounded. Okay, bounded. You won't increase, you will be bounded. Okay, but this bound depends on the selection of K3. If you choose a larger K3, this error will be smaller because, and you will track this trajectory, trying to track this trajectory. Okay. Okay, and this give you, this tell you what V value eventually will be. Okay, because V0 is from here and it will be UB. Okay, and this value, this UB value determines what this is. Right, because there is a relation, E and R. E could be -2, so I should put this absolute value. Okay, because it's square here, square here, square here. Okay, so given a V value, you can only find R squared, E squared, not R or E, okay, only squares. So I put absolute value here, okay? V is always positive, right? V is always positive because you have R squared, E squared. And when you trying to infer V to your error signals, you need to put absolute values because from here it's always positive. So how do you find this? According to this, okay, you know, approaching to 0, okay, at the approach to 0, that means V dot is equal to 0, right? When it's in here, V is almost constant, right? 如果 V is constant, V dot will be 0, right? Right? And you just let this, although it's an inequality, you let this one to be 0. Okay, you want phi beta to be 0, right? To get this value. But it's so the best you can do is not equality here. Okay, it's not equality here. Okay, it's upper bound here, right? It's upper bound. You only know the beta upper bound, right? You don't know what beta really is. You know the upper bound, but so the only thing you can do is set this to be 0. Okay? And you can find where is R, where is R, where is E. Okay? 我们把两个合在一起. So let's put let's further upper bound this by minus minima K2 and let's take the coefficient out, okay? And let's ERZ square plus okay. Let's combine E and R into one parameters. Okay, that's easier to find the upper bound of both signals. Okay, 听懂吗? And you have put minima here, minima of these two values. Okay, you compare the two, and if this one is smaller than this one, and the whole term, you choose the minima one. Okay, you choose K2. If this term is smaller than K2, you choose this one. Okay, 听懂吗? 听得懂吗? And you put minima because there's a minus here, so that you can upper bound this inequality. 听懂吗? 懂吗? Any questions? You can upper bound this, right? Use this to upper bound this, right? Okay, so and we put this one to be 0. That gives you Z norm square to be right? 对吧? You put this to be 0. You put this term to be 0.
The mean has to go to the denominator.
Oh, right.
Technically,
this, right? Okay, so so I'm wrong here. It's hard to evaluate what E is, or what R is. The best way is to combine both to be Z. So you can only observe Z here. Okay. Okay, Z, but it can be considered as an error. Okay, and we now know this value. This value is equal to the worst case. This value is equal to this. Make a square root. Take this square out. Okay, this is the value that's this is the worst case UB value. Okay, 这样懂吗? worst case means v dot, this upper bound v dot, okay, is not equal, it's upper bound. And we put the upper bound to be 0, which means this is the worst case. Okay? 懂吗? We only know the upper bound of v dot. Okay, and we put the upper bound to be 0. So this is the worst case. Okay, in reality, v could be smaller than this, but this is the worst case value, the highest value. Okay, so and there are many physical meaning of this value, right? You see K3 here, K3 here. If you increase K3, this value will decrease, right? It will decrease, right? Means if you increase your control gain, VR here, okay, K3 here, which is in VR, this value will decrease. So is this value will decrease. Okay, so you can make your Q more close to QD. 我要找 V， 它等于0的时候，这个它的 R 和 E 会到哪里嘛？懂吗？我要让这个等式等于0，我要去找最小的 R 跟 E 是在哪里。但你不 combine 在一起，我无法找出来。我知道 combine 在一起，这样我就可以求出它的解的嘛。因为不然你两个 variable，you have two variable R and E。And only one equation, how can you find E and R? There are infinite number of solutions, right? So the worst case is just so the way is put the two variable reduced to one variable, Z. Of course you have to compromise something, but at least you know what Z value is eventually, right? According to the V value, you know what the Z value is, okay? Z 的弄就是这个 variable 的弄啊，你就看成你就看成 x y 嘛，那1 2 z norm is if m is time variant, when you take the time derivative, there will be a dot here and one more term, right? So it will be more complicated. So you change the definition of our problem, okay? So the question is, if m is measured, if m can be measured, and what will happen, right? So basically, they change our assumption here. So they change the problem here, okay? 那是另外一个问题. So that will be the previous case with exact model knowledge. Okay, so the control design will be easier.
如果那个 K3 变大，那它 UV 的那个值还要小，会怎么样？
没有，你这
decrease 会那个 UV decrease 会怎么样
？So this value is the UV value. It tells you when what's the minimum value of V will be, right? In a steady state, eventually V will reach to this value. So if you increase K3, this value will decrease. Yeah. And the decrease of this value can also decrease this Z. No. Okay.
这样不是误差变小？
那很好啊。
所以K3 越大越好。
Right. This why it's called high gain control. Right? High gain control. 这边有问题吗 ？Hello， 你们有问题吗？
老师 K3 有什么限制
？K3 有限制啊。
可是说它要到多大？
你就 choose 啊，你要在你控制器有限可以，你 K3 越大，你的 K3 越大， K3 越大，你的什么 control output 会越大嘛？你 K3 越大，就是 VR 越大，你的 required torque will be increased. If K3 in increased K3, required torque have to be increased. But your controller usually, for example, you control a motor. The control input torque Q here is the current, and the power module have limited current, right? If the required torque is over the maximum value, maximum output of the controller is not feasible. Okay? 这样 area 可能就变大，比你想象还要大，对啊。The question is, if I know M, if I know Q double dots, well, you might simplify your controller design, but not here, but not this case.